We have now reached the final validation stage in the model based design journey, where virtual meets reality and simulation finally touches the road. Welcome to Vehicle in the Loop or ViL, the phase where a real vehicle interacts with a simulated world to test systems safely and accurately before they hit the street. If Mill and Sil were software based and Hill was hardware based, then ViL is the hybrid bridge. It combines the real car with virtual environments and test systems. In simple words, the vehicle becomes part of the loop. It's physically running, but the world it drives in, the traffic, obstacles, pedestrians, road conditions can all be simulated in real time. Imagine your test car parked in a lab or on a test track. Inside that car sits the same ECU, sensors, and actuators that will go into production. But instead of driving on real roads, the inputs to those sensors, like radar echoes, GPS signals, or camera feeds, come from a simulation computer. So the ECU thinks it's driving through a real environment, while in reality, everything around it is being fed digitally. This is the vehicle in the loop concept, a controlled fusion of a real and virtual worlds. The car runs exactly as it could on the road, but engineers can test a dangerous or rare conditions like pedestrians suddenly crossing, black ice on the road, or a vehicle cutting in without putting anyone at risk. How will works? In a will setup, three main components work together: the real vehicle, equipped with the production ECUs, sensors, and actuators; the simulation environment, generating road, weather, and traffic scenarios in real time; the interface system, which connects the real vehicle signals with the virtual world, translating between physical and simulated domains. The car sensors like radar, lidar, or cameras are either fed synthetic signals or connected to virtual sensor emulators. For example, a radar sensor can receive simulated reflections from a digital car in front. A camera can get a video input from a real time 3D simulation engine like CarMaker or DSpace ASM. The GPS system can be fed virtual coordinates as if the car is moving. Meanwhile, the ECUs and actuators respond naturally, accelerating, braking, steering just like in real driving. These responses are fed back to the simulation environment, closing the loop. Everything happens in milliseconds, maintaining real time accuracy. Why will is so important? Will is the last stage before real world validation. It ensures that all the systems, logic, and interactions work perfectly when everything comes together. It's especially critical for ADAS and autonomous vehicles, where the system must interpret complex environments and make safety critical decisions. With will, engineers can test pedestrians crossing under rain or fog, sudden lane changes, stop and go traffic, emergency braking, or evasive maneuvers, all without risking real lives or damaging cars. In essence, will lets you to drive thousands of virtual kilometers safely in a lab while still collecting data as if the car was really on the road. 10 things verified in vehicle in the loop. Sensor fusion accuracy. Validating how radar, lidar, and cameras work together in mixed real virtual scenarios. ADAS and autonomous logic. Testing adaptive cruise, collision avoidance, lane centering, and emergency braking. Vehicle dynamics interaction. Ensuring the control algorithms match actual mechanical behavior. Communication bus verification. Checking CAN, LIN, or Ethernet data flow between ECUs in real time conditions. Timing and latency. Verifying system delays between sensor detection and actuator response. Environmental robustness. Testing under simulated rain, fog, night lighting, or icy roads. Safety and redundancy validation. Ensuring fail-safe work correctly when one sensor or ECU malfunctions. Human interaction with the real controls. Measuring how the driver or operator feels during ADAS engagement. Closed loop vehicle testing. Verifying full control chain from perception, decision, and actuation. Certification and regulation readiness. Providing traceable logged test data for compliance ISO 26262, UNECE R157, etc. Let's say you are testing automatic emergency braking on a prototype vehicle. In ViL, the vehicle is stationary inside the lab. Its radar sensor is connected to a simulator that generates a virtual road scene. A vehicle ahead slowing suddenly. The radar sees that digital car and sends the distance data to the ECU. The ECU calculates that a collision is imminent and activates the brakes. Even though there is no real vehicle ahead, the braking system reacts exactly as it could in real life. Engineers observe brake pressure buildup, timing delays, and ECU decision making, all while keeping the test perfectly safe and repeatable. Let's talk about the power of mixed reality. Will isn't just a simulation, it's a mixed reality engineering. It allows engineers to fine tune systems that depend on both the physical world and digital perception. Think about autonomous driving, where decisions rely on camera, radar, and LiDAR interpretation. If those systems fail to recognize a shadow, reflection, or unusual object, the result could be dangerous. Will lets you recreate those edge cases from dazzling sunlight hitting a camera lens to unexpected objects on the road. So algorithms can be improved before real testing. Integration with other loops. Will does not work alone. It's part of a chain. Each loop feeds into the next. Mill ensures your control algorithms behave logically. SIL checks that your code run correctly. PIL validates your code on the real processor. IL connects your ECU to real hardware. DIL brings in the human driver. Will connects the entire car to the virtual world. After Will, you move to real world proving grounds or public road validation. But by then, 95% of the issues are already caught and solved. That's the power of model based development. You move from idea to vehicle safely, efficiently, and confidently. Here are some of the most popular wheel setups and tools in the automotive world. These systems connect simulation computers with the real vehicle ECUs, sensors, and actuators using ultra low latency interfaces. They are capable of generating full traffic environments with 3D visuals, road geometry, pedestrians, and weather, all synchronized with the real vehicle's control systems. Let's talk about benefits of vehicle in the loop testing. Safety. Simulate dangerous scenarios without physical risk. Cost efficiency. Reduce prototype and track testing expenses. Repeatability. Test the same event hundreds of times for validation. Regulatory compliance. Generate detailed test evidence for certification. Speed to market. Shorten development time through early issue detection. In short, will helps manufacturers validate vehicles faster, safer, and smarter. To wrap it up, vehicle in the loop is where the real car meets the virtual world. It's the final rehearsal before the curtain rises on real world testing. Engineers can validate how sensors, ECUs, actuators, and even the driver interact with the dynamic environments without ever leaving the lab. From algorithm design in mill to full system integration in will. This entire journey forms the backbone of modern automotive development, reducing risk, cost, and development time while ensuring absolute safety and performance. So, the next time you see a self driving car or an advanced driver assistance feature working flawlessly on the road, remember it's not magic. It's the result of thousands of hours of model, software, process, hardware, driver, and vehicle in the loop testing behind the scenes. And that's how every new car system is born. Not just through design, but through the digital evolution of testing itself. From code to car. This is how engineers bring intelligence to motion.